Hello, Futura Camp. My name is Connor. I'm a dev who's focused on Zcash. Specifically, I am part of the Tachyon team. We are developing what is essentially the fourth version of Zcash's shielded protocol and zero-knowledge proof system. However, this talk is not about what's coming. This talk is about Orchard, which is the current production shielded protocol in Zcash, which is the third version of Zcash's shielded protocol. And specifically, we're going to be talking about where to look for a privacy backdoor in Orchard. And Zcash is an open source privacy project, one of many open source privacy projects. And if you think about it, there really is no open source privacy project that escapes conspiracy theories. Whether it's Signal or Tor or PGP or other privacy coins, you can always find someone who is going to be paranoid and make up conspiracies about it. And Zcash is no exception. And if you listen to what the conspiracy theories and criticism on Zcash are, you find a lot of different things. So like, when researching for this talk, I found a lot of discussion about if there are soundness bugs or if users' funds are safe, and a lot of criticism about how it's too hard to use it in a privacy-preserving way, if most people don't use it in a privacy-preserving way, or things like that. But really, this talk is about if it's possible at all to use it in a way that's private, and making sure that there are no privacy backdoors in the real, truly private, like, best way to use it. So, you know, that would be when you use Orchard and you transact within Orchard. So many of you might know Zcash has a transparent pool, and then it also still has, you know, Sapling and Sprout, the version 2 and the version 1 pools that are still usable in some capacity. But for the sake of scoping the talk, we only want to look at Orchard to Orchard, also known as Z to Z, not T to Z or Z to T or T to T. We're looking at when you do it right. The talk is also specifically focused on privacy. So we're going to ignore and talk about, or save it for another day, all the concerns about soundness. So if there's some backdoor that would allow people to mint Zcash or to steal Zcash, that's a different talk. Today we're only talking about privacy. And my goal with this talk is to teach you, since if we actually walk through every line of the code, we would be here all day. So with the short time we have, I hope to educate you on where to look in the code and the specs yourself, if you are paranoid and curious. So like I said, in this talk, out of scope, we're not going to talk about any attacks on things besides privacy. We're not going to talk about wallet and network layer security because, you know, we can prove that the protocol is super, super secure and super, super private. But if you have a wallet that sends everything to Jeff Bezos, then, like, you're screwed. But, like, we'll consider it a success if it's possible to build a wallet that is secure. We're also going to leave user errors out of scope because with every privacy tool, there are ways that the user can mess up and end up leaking information. In our case, for example, what if a user accidentally uses the transparent pool when they intend to use the Orchard pool? That's out of scope. For this talk, we're going to assume the user mostly knows what they're doing. And lastly, a lot of the criticisms I found were just like the words of various people who have contributed to Zcash over the years. So that's obviously silly and not worth talking about. Hundreds of people have touched the code in the 10 years that the project has been around. So let's get into it. We can agree that when you use a privacy coin with, let's say, a mobile wallet, your device has some secrets on it. Your phone shows you your balance and maybe some information about your transactions, and you don't want that information going to the public internet. I think we could all agree. If your secrets go to the public internet, that would be bad. We would already forget about a backdoor. If your secrets are going to the public internet, that's worse than a backdoor. That's the whole world can see what you're doing. And we would probably know. So we would probably know if there was a bug like this. Like if you could find my secret data right now on your laptops from, say, the Zcash Block Explorer or maybe from the mempool or the P2P network, let me know, because that would be very bad. Instead, what you have is some data that leaves your phone that doesn't leak your secrets. It looks jumbled. It looks like ciphertext. This is what should go to the public internet when you transact in Orchard. And assuming the text is jumbled or encrypted or whatever, we're good, right? Well, don't take my word for it, because we still need to make sure that there's no adversary who can take the jumbled ciphertext that leaves your device and can somehow get your secrets out of that ciphertext. So that is what we are going to get into for the rest of the talk. We're going to examine the structures of the data that leaves your device when you send a private transaction, and we're going to go over all the things that make it hard to get the secrets out of that ciphertext. So I went ahead and I went on the Zcash Block Explorer, and I took a random Z to Z Orchard transaction from a real mainnet block. It's this one right here. So if anyone in the audience sent this transaction, maybe you recognize its hash. You can see from the Explorer that it is a shielded transaction, and you can see on the right-hand side, there's a couple different transaction types when you go to the Zcash Explorer to look. Like there's a de-shielding one above, which is a Z to T. There's a couple public transactions, and then at the top, there's a Coinbase transaction from a miner. The one that I circled and that we're going to be digging into today is a fully shielded one. So we shouldn't, if the protocol works, we shouldn't be able to learn anything about the sender, recipients, or amount of the transaction. So I downloaded it. I downloaded the circled transaction from one of the full node RPCs, and this is what I got. It's 37 kilobytes when it's JSON serialized, and you can see some of its values printed out on the screen here. And the question is, does anything in these 37 kilobytes leak the user's secrets either to us, people who just are looking at the network, or to someone who has some kind of secret key, someone with a backdoor? So we're back to our analogy here, but now now we have a closer look at what the data leaving the device actually is. Question?
Is the text that the user sends to the chain?
Yeah. Yeah, so this is, the transaction is what leaves the wallet when you transact. So our assumption is that this thing that you send does not, or that there is no way to get secrets out of this thing that gets sent. So can the adversary get the secrets out of this object here? Now, we're going to call it out of scope for this talk because the wallet does have to query a bunch of things from an RPC. In order to create a transaction, you need to update your wallet's witness which involves making some requests and getting some responses from the RPC. And there are foot guns there. There are ways that you can leak more information than you want, metadata-wise, when you talk to the RPC. But we could, for the sake of the talk, just say, oh, you're using a full node, or oh, you have really good OPSEC. And in practice, there are a lot of safeguards in the wallet that keep your metadata safe. So we're going to, again, narrow our scope to just what's in the transaction. So remember that 37 kilobyte JSON object. There are 26 fields in that JSON object. And the Orchard data is segmented into individual actions. So there may be, depending on what your transaction is, if you're like spending a lot of inputs, creating a lot of outputs, you may be able to have like more than 26. And of those 26 fields, we have 13 that are totally unrelated to the sensitive data. So these are things like the version of the transaction you're sending, the block hash, the block height, et cetera. And none of this should leak anything sensitive. Then you have 6 fields out of the remaining fields which are pertaining to the transparent pool and pertaining to the sapling and sprout pools. And these should be empty if you are doing a Z2Z Orchard transaction like the one that we downloaded, and they are in the one that we downloaded. So 7 fields plus the action fields remain that we need to look into. And these are the action fields and the bundle fields. So every Orchard transaction has a few bundle fields, and they all have at least 2 action fields. And this is where looking for a backdoor actually matters. So the action fields are all computed from your secrets. And we have here 8 of them. So you need to look into how all of these are computed and make sure that there's no way to backdoor any of those computations. So the question becomes, can an adversary take these 8 values and get your secrets out of them? So what are the secrets, or what are the structure of the secrets? We have these objects called notes. And the notes are the secret values that include the recipient, a value, and a couple like random values that are created for security. And these are the things that actually get encrypted. And like, long story short, these are the things that we want our protocol to keep safe. I circled recipient and value here because those are the sensitive parts. There are 3 cryptographic building blocks that protect the secrecy of your notes. And these 3 things are hiding commitments, encryption, and zero knowledge. We will get into what all these things are. First, we have Peterson commitments. And a Peterson commitment is a like random looking value that binds a clear text in a way that is impossible to figure out what the clear text is from the Peterson commitment. And Zcash Orchard uses elliptic curve-based Peterson commitments to bind clear text in a fully privacy-preserving way. and do your own research, but these things are regarded by mathematicians as perfectly hiding. I won't get into the math of why they're considered perfectly hiding, but you know, if you're paranoid and curious, look into it. Of the 8 fields, one of them is nullifier, and here we show how the nullifier is computed from your secret data. So this value, E40F5E9 and so on, is from the real transaction that I downloaded off the mainnet. So if any of you can figure out how to get NK or CM out of it, please let me know, because you would have just found a privacy vulnerability in Orchard. CM is computed from the secret note, and NK is computed from the user's wallet. So basically, we trust this computation here, extract P, and so on, to obfuscate the sensitive information and produce a value that no one can get the secrets out of. So if you're looking for a backdoor or privacy vulnerability, this is one place to look. Poseidon hash is part of this computation. As you can see, we Poseidon hash that NK value. So the Poseidon hash is a cool place to look for a backdoor. I wrote a little bit about how Poseidon gets instantiated, and there are these magic numbers in Poseidon and in every hash function. And so if you're paranoid, look up how they did that. It says in the Zcash spec that they use the LFSR, the grain LFSR procedure from the Poseidon paper. If you're paranoid, double check that. It's probably fine. Okay, RK is another value that appears in the transaction. And in the one that we downloaded, it starts with 361 BEAD. So again, RK is computed from AK plus alpha times G. AK is a secret. So if you in the audience can figure out the user's AK from this 361 and so on value, you would have broken privacy. But you shouldn't be able to do that, because AK is a number, and we add another number, and there are infinitely many ways to have 2 numbers that add up to this value. Spend auth sig is another one of the 8 values, and the one in our test subject transaction starts with 79DC. And this is a elliptic curve digital signature. So if a signature scheme leaks private data about the secret key, it would be a really bad signature scheme. You'd be able to spend funds if this had a privacy vulnerability. Then we have CV. Again, this one does some hashing, and it's basically the same as the other ones. I'll just blast through these real quick. Here's another one, CMX. This is the X coordinate of the note commitment that gets added to the tree. And these values here in red, GD, PKD, and V, are sensitive. And this is a little weird, right? So you see that this particular commitment is computed with a function called synsomia. And it would be a privacy vulnerability if you could get those red values out of this. So this is different than Poseidon hash, and it's different than Peterson commitments. So this is an important place to look, like learn about Synsomia and decide if you trust it. And that concludes the part of the cryptographic building blocks that protects your privacy using commitments, hiding commitments. Next, there's the encryption that protects your privacy. So this is, in my opinion, the most sensitive part of Orchard to audit because, worth mentioning, Tachyon, which is our next iteration of the shielded protocol, eliminates this entirely. So if you don't trust Orchard's note encryption, just wait for Tachyon, and then you can use whatever encryption you want. But Orchard encrypts the notes with ChaCha20 poly, a key derivation function, and a Diffie-Hellman shared secret. And you can see that the Rust crate for Zcash note encryption imports this ChaCha20 cipher, and libsignal also uses that same thing. That's not a reason to trust it in and of itself. You still should do your diligence, but it is a strong library. And then the third thing that protects your privacy in Orchard is zero knowledge. So part of that 34 kilobyte JSON value that we got off the Block Explorer is a 14.5 kilobyte ZK proof. And it would be the subject of a whole other talk to talk about how zero knowledge proofs work. But you do need to consider if there is some way to take that 14.5 kilobyte proof and get the secrets out of it. All the public inputs, those 8 fields that are exposed in the transaction object, go into the zero knowledge proof system, and a bunch of sensitive stuff from the secret notes also goes into the zero knowledge proof system. It is paramount to the integrity of the privacy system that the proof system has a formal property called zero knowledge. So if you're curious about that, you should read the paper that proves that the Halo construction has zero knowledge, and then make sure that the code that is actually deployed follows that formally proven property. And that would be, again, the subject of a whole nother talk. But thankfully, I do have a post on my blog that explains and attempts to demystify what the formal definition of zero knowledge is. So if you're curious about that, go read my blog. And that is all I have for today. Sure, yeah. Any questions?
There's a lot of liquid curve cryptography there, so what about, is there any thoughts around quantum security in the Zcash world?
Yeah, so quantum vulnerabilities are not backdoors. That's like a different thing. But what you want is you want to make sure the encryption is quantum resistant. And with Orchard, it's actually not. The ChaCha cipher or something about it is quantum vulnerable. There are other mechanisms that protect a quantum adversary from being able to learn the whole transaction graph. So like even Zcash Orchards has some privacy protections against a quantum adversary, but it's not perfect. So in Tachyon, we aim to solve this by basically just letting you use whatever encryption you want. And I believe one of the partnered orgs is working on a like fully quantum resistant like note secret dispersion system.
Or they're all only related to the encryption part?
Yeah, so the Peterson commitments should be quantum safe. That's part of them being considered perfectly hiding. And the hash functions should also be quantum safe.